Okay, try again. Thanks very much for the introduction. So as you heard, I wanted to start off by explaining I'm not actually involved in the space sector by history. I'm a chartered civil engineer, so I'm used to doing things on the ground. I designed and built lots of tunnels, bridges, and worked in construction on a lot of very traditional engineering projects. But I also did a lot of work on upgrade, maintenance, inspections of bridges and other key infrastructure assets. And part of going through that process kind of drove me to this idea that I'd do a little bit of research and see what other new technologies could support civil engineering. So my research is in collaboration with a whole bunch of different organizations, but it essentially brings the civil engineering side together with the space industry, so Earth observation, remote sensing, and satellites. And I'd like to start this presentation by telling you a story. So one Friday afternoon, a train driver was taking passengers across a bridge somewhere between Dublin and Belfast in Ireland. It's Friday afternoon, it's after work, so the train is heaving with passengers, and he crosses over a bridge called Malahide River Viaduct over Broadway Meadow Estuary, a large body of water. As he's driving over this bridge, he notices the water next to him splashing a little bit higher than he's used to. As he looks out the side of the window, he notices that part of the bridge is collapsing beneath him, and he could see the bridge physically collapsing beneath him. Luckily, in that instance, he was able to coast the train over the bridge before the collapse occurred, but this was the end result. He called it in before any further trains could pass. So as I mentioned, this is the Malahide Rail Viaduct in Ireland, and it collapsed in 2009 due to something called scour failure. So this is something civil engineers are well familiar with, but in case you're not, scour failure is the wearing away of riverbed material. So if a bridge's foundations are sat on the riverbed material and it's scoured away, as in eroded underneath it, a hole forms, and then the bridge foundation is no longer supported, and in that case, scour occurred and the bridge collapsed. But bridges don't fail just due to scour. So this was in the US. This is the I-35 West Mississippi River Bridge, which collapsed, and collapsed, killing many people, after which a forensic investigation was undertaken to investigate why this collapsed and what happened. And the scary thing about this particular incident was that in inspection photos, you could see parts of the plates starting to bow out, indicating that there was a problem. It was just that it wasn't spotted. And the issue is that, in reality, visual inspections is very useful for spotting anomalous behavior, but it also misses many things. And these aren't isolated incidents. We're hearing more and more bridge collapses globally, and here is a kind of few newspaper titles just from the last 5 years, just in the UK, just on scour failure. So it's a problem that many people, especially the general public, don't realize is happening. A lot of questions I get asked is, why study bridge collapses? Are there really that many collapsing? And the answer is, well, apparently so. So these are all photos from when I was a design engineer, all from bridge inspections in the UK, primarily rail-related assets. And essentially, if you've ever done traditional bridge inspections, you take your drawings, you turn up on site, you try and note as many defects, take as many photos as you can, and then you take those drawings back to the office. From there, you can then model your bridge asset with some assumptions based on the amount of deterioration you've seen and do a full bridge assessment. But the reality is this relies on people being able to spot problems. A report by the Federal Highways Works Authority identified that actually there are a number of flaws with visual inspections, and if you read through the report, it cites things such as what the weather's like, whether it's a cold day, whether the inspector is colorblind, are they hungry. All of these things play an influence on how well you're able to spot things. So that's a little bit about the motivations behind my research, and that's why I've ended up trying to make use of our so-called eyes in the sky. So there are many, many different satellites out there, and my focus is primarily looking at a technology which makes use of radar satellites. So these are two radar satellites owned by the German Aerospace Center called TerraSAR-X. And using TerraSAR-X, we can take advantage of a technique called Interferometric Synthetic Aperture Radar, or InSAR. So very briefly, and this is a gross oversimplification of the technology, but it's roughly what happens. The satellite passes around over the Earth and actively emits radar. The radar bounces off objects and then is collected back up on the satellite. Now, if the satellite goes round and round again, it can keep collecting a series of measurements over time. So the first time it takes a measurement and bounces back. If the object moves, the amount of time the radar takes to travel there and back increases, and there's a change and shift of wave between each of these images. Using that principle, you can then equate that to an equivalent distance and measure displacements in the line of sight of the satellite over time. So the picture on the top right is a raw radar image. It looks a little bit like a black and white picture, and what this picture shows is actually the amplitude. So things that are bright and very reflective in white, and things that are water bodies tend not to reflect very well, so they're quite dark. And so the technique basically stacks a series of these images, one on top of the other, and tracks points that are quite bright, stable, and reflective over time. So things like buildings, bridges, the built environment assets reflect very well and provide a stable, coherent reflector. Things like farmers' fields or the tops of tree canvases, they move around too much to provide any kind of stable, coherent point that we can continuously track over time. And so the kind of output that you'd receive from this analysis is shown on the bottom right. So each of the points marked are what are called persistent scatterers or permanent scatterers that are a stable reflective point over time. And for each of those points, we can track their movement. So some of the applications that we'd use this for. This is the Bank area in London. So the Bank underground station underwent a remodeling, and new tunnel lines were dug. And during tunneling, obviously the surface profile above the tunnel settles, which is an expected effect. And you can see this here compared to the rest of the points. There is a profile of settlement. So a piece of work was done to look at the comparison between traditional surveying methods and what a satellite could do. And we monitored many different points over time. Notably, satellite measurements can pick up millimeter scale movements. The unfortunate scenario is that we can't always control what points we're measuring. So if you want to perform a like-for-like comparison between the tops of a facade of a building, you can't always necessarily control that. In certain examples, which I'll go on to later, you can identify points by installing an artificial reflector to reflect the radar. So back to this example of Malahide Viaduct and Scour and these types of failures. Scour is one of the key concerns expressed by UK and US bridge owners. And one of the main problems is the ability to inspect this kind of failure. Very often you have to send a diver to inspect for scour holes beneath a bridge. Now, this presents two problems. One, when a bridge is most susceptible to scour failure is during flooding itself, which is a dangerous time to send a diver. Secondly, if the water is murky or parts of the riverbed are kicked up, you might obscure the scour damage itself and therefore not actually see signs of the problems. And so this is what happened in the case of Tadcaster Bridge, which was regularly inspected but ended up failing after a period of heavy flooding in December 2015. So, Tadcaster Bridge, it's a car and pedestrian bridge. This is what it looked like before it collapsed. It's about 100 meters long, 10 kilometers wide. And actually, someone caught the collapse mechanism of Tadcaster Bridge, showing that the middle pier of the bridge collapsed with a pronounced dip in the middle, as you can see the pier below it giving way, until finally the whole bridge collapsed. So, one exercise that was undertaken was to take historical archive satellite data that was collected prior to this collapse and analyze it to see whether we could see signs or precursors to failure. So this is Tadcaster itself, and that's the bridge you can see after collapse. But the radar imagery was processed for a 2-year period prior to this, and the points of stable reflection were collected. So those points over the bridge were then plotted over time so we could look at the behavior. And the results look a little bit like this. So, as a little bit of explanation, each of these points relate to a point on the bridge. The point in red relates to an area which corresponds to the collapsed area of the bridge. And what we can see is that generally there's a little bit of noise, but a fairly stable period over time. And then, during the period of flooding, this point in the middle starts to dip a little bit, and then a little bit. But the interesting thing to note is that both of these points, which are kind of identified as anomalous or outside the region of normal behavior, both happened in the month or so before the collapse itself occurred. So there was a kind of sign or precursor before the collapse itself. And to be fair to the bridge engineers of this bridge, the size of magnitude is not huge. In a 100-meter long bridge, you are unlikely to be able to identify a 10-millimeter dip in a bridge. So as I said, that red point related to that point on the bridge, which eventually was the pier that collapsed. So other than predicting failures, other studies that I've looked at in the last few years have included what we can do in terms of regular monitoring of bridges that may not collapse, but we want to understand their behavior a little bit better. So Waterloo Bridge is a major bridge in central London, spanning the River Thames, and the owners, Westminster Council, wanted to understand, they had a few suspicions about potential problems and wanted to monitor the bridge. So they installed a monitoring system across the bridge with a number of displacement sensors, but also total stations with target prisms. The target prisms were put on top of, in the central spans and on top of each pier. Now what I wanted to do is compare what a total station measured with satellite data to see what we got. And so as I mentioned, what you can do is install a corner reflector. A corner reflector is a cheap piece of, say, aluminum metal that creates an artificially strong reflection point. So that the satellite radar will reflect off these, and we can track a known point over time. So, as I mentioned, each of the piers were fitted with a total station prism, and alongside each total station prism, I installed a satellite corner reflector. And you can see from the previous image, they're not very big and they're not very obtrusive. The only requirement that Westminster Council wanted to have was that it was not at the top of the bridge so that the public couldn't, reach it or grab it or do anything to it. In reality, someone managed to throw rubbish into one of them, so I don't know who was leaning over the side of the bridge and playing toss your rubbish over it, but I don't know, people are always a bit of a risk with monitoring systems. And the results actually show that the satellite data ties quite well. So just as an explanation, the points in pink are the satellite data. The blue lines are from the ATS, traditional total station surveying, and the orange line is the temperature. So what can we see from this? Well, satellite data can be used to show seasonal movement over time. The readings are actually taken in a period of every few days, depending on the satellite, so maybe 6 days or 4 days, or it depends on the satellite constellation you're looking at. So you can't see daily variations. And actually, when you spot a direct comparison on the day between points, there is some noise and there isn't always full correlation, but it can be used to show signs of overall behavior, which do correlate well with seasonal deformation. Another example I'd like to highlight is Hammersmith Flyover, again from London. It's a concrete bridge that was closed in December 2011 because of worries due to pre-stress corrosion. So pre-stress corrosion is not something you can really spot from radar on a satellite, but as part of these works, the bridge was fully instrumented, and it was noticed that a few of the bearings were jammed, stuck. So if these bridges, if the satellite radar can be used to monitor what is normal behavior over a bridge, or we can establish what is normal behavior, can we spot when something anomalous, such as a bridge bearing, doesn't work anymore? So as I mentioned, Hammersmith Flyover was also instrumented with a structural health monitoring system, initially by academics and by consultants who were brought on to design the remedial works for the bridge. And then I, on top of that, processed archive data collected over the bridge from the last 8 years. And this was the rough output. So I found that there were a number of points along the edges of the bridge. There are some gaps that was attributed to shadows. So if a satellite it's quite steep in angle, but if there are tall buildings or skyscrapers in areas like London or heavy urban areas, you do get radar shadows where the radar can't physically reach the asset. So it's worth understanding the geometry and orientation of your bridge and noting that it's not suitable in all cases. Next, I wanted to understand how we could integrate this with current digital environments that civil engineers and asset owners use every day. And also help it with that interpretation. So that in that overlay, we kind of use a base map. It could be Google Maps or OpenStreetMap or whatever it is to kind of understand some physical interpretation of what our reflections are coming from. But we in the civil engineering world are getting used to BIM environments, 3D modeling environments, and also bringing, as we heard from earlier presentations, bringing the geospatial component into that. So if we use things like our BIM models, and openly available data. So this is Ordnance Survey data, which is available in the UK, which gives 3D elevations of the surrounding buildings, and maps as well. And then import the satellite data in all of this environment. It can be used to better understand what the satellite data is reflecting from, but also understand what we're able to monitor. And one of the things that I've kind of come across with satellite Earth observation data, and a lot of it is being sold nowadays, but one of the things that is lacking is this integration with the systems we already use. As it was mentioned in one of the presentations this morning for the Crossrail project, having a number of different systems, but everyone being able to play in the same sort of space is incredibly useful. And that's how we derive value from this kind of data. So back to monitoring bridge behavior. Using the satellite data interpreted with some 3D modeling understanding, and then on top of that, using the understanding of the structural expectation of behavior, we can use that to monitor satellite points over time. So for this particular example, we know that the way Hammersmith Bridge was articulated is that the primary loading case is temperature. It's temperature-driven movement, and the bridge expands and contracts primarily in the middle and less towards each abutment. So we know that the bridge expected movement is somewhat similar to Waterloo Bridge in that it oscillates over time. So out of the points that were attributed to the bridge, we can pick out the points that oscillate over time in the area of each pier and then plot the pier displacement patterns against the temperature displacement patterns and the satellite displacement patterns, and attribute satellite reflective points to what we know to be pier movements. And through that, we were able to identify which piers were oscillating less than other piers, and therefore which piers were stuck. Luckily for this set of data, we were given satellite data for a period that covered bearing replacement. So you could see the satellite data before and after the bearing replacement and see that it was, in fact, able to show that the bearing had ceased, almost in reverse effect. So rather than showing that a bearing had stopped movement, we had movement that was stopped, and then after replacement of the bearing, it showed that the movement was able to go forward. So this is I quite like it, it's quite a pretty picture, but it's a radar differential interferometry radar image of London, and it's basically the 2 points, 2 different images subtracted one from the other. But the point of the image is mainly to show that actually one single image is quite large area. So for each of the case studies I showed in London, they were all taken from subsets of a single image. One footprint is the size of a large city. And the fact that these satellites operate in polar orbit means that they're going around and around, which means that technically they cover every area of the Earth. There are some limitations in thinking about using archive data, in that if the satellite wasn't switched on, there's nothing in the archive. So all previous failures and studies can't actually be investigated using this data because it depends on what data was actually collected. But the resolution of the data is getting much better and better. When this first started in the 90s and into the 2000s, the older generation satellites had pixel sizes of 30 meters or so. which meant that it's useful for large-scale deformations like earthquakes and volcanoes, which is where this technique started, but it's not really useful for urban remote monitoring situations. The new generation of satellites launched around the 2007 time, and new ones launched by the European Space Agency, means that the resolution is finally at a stage where we as civil engineers can take advantage of this monitoring information to monitor urban environments. So, for example, commercial satellites have pixel sizes that could be from 3 meters down to half a meter, and the European Space Agency has launched a couple of satellites that give you radar pixels of 10 to 15 meters, but the data is freely available and accessible by anyone who wants to use it. The daily revisit time between satellites is getting smaller and smaller. If you have one satellite traveling on its own, it takes images X number of days, but if you put 2 satellites in tandem, that amount halves. So the resolution is getting better, the number of readings is getting better, and the price is dropping or is becoming more openly or freely available, which indicates we as civil engineers are at a point to really make use of this data. And although I indicated there are a number of problems and limitations in how we use this data and how we make use of it, if we start understanding it now, as the price drops and as the resolution gets better, we'll be in a very good place to make the most of this technology. So, in summary, this increasing in temporal resolution of the data will provide us with new opportunities for infrastructure monitoring. In a time where we're now at visual inspections in a period of years, so in the case of, say, UK highways, bridges, we inspect bridges every 2 or 6 years. Every 2 years, we're close enough to physically see the bridge but not touch it. Every 6 years is a principal inspection, where we're close enough to physically get in and look at every part of the bridge. In the period between that time, we stand to gain from satellite insights to give us some understanding or maybe some precursors to failure warnings. To make use of that, we as civil engineers need to understand the opportunities, the errors, uncertainties, and limitations, and this shouldn't be left to the Earth observation community, who are primarily driving this field of research, without an understanding of what we as civil engineers want to know about our assets. As I've indicated by Tadcaster Bridge, there are promising signs to monitor for precursors to structural failure. And finally, there's a real opportunity to link with existing BIM or other asset management practice systems so that this doesn't become a kind of side application, but could be integrated into the systems that we as civil engineers and asset owners use every day. Thanks very much.
Thank you very much for a very interesting presentation. If there are any questions, please, now is the time. Sakthy is here. Maybe just a question, how problematic the shadows are. So is there a GIS map where you can see what actually you can measure without shadow problems and things like that? Yeah, there's a couple of problems. There are issues in shadows, but also in what does and doesn't reflect well. So for certain objects, things like steel bridges or parapets reflect really well. Some masonry arch bridges don't reflect very well at all. So there's a couple of options you can do. You can either retrofit with these reflectors, but to understand what does and doesn't have a shadow, you kind of have to run a simulation. But again, that's where, like, if we have started integrating things into a digital environment, like a BIM model or 3D elevation model, you can, without having to purchase and run all this analysis, you can simulate the effect of a ray because you know what angle the radar ray is being sent down, and you can simulate what would and wouldn't cause a shadow. So in that example with Hammersmith, where there was a city and there was a bridge in the middle, you can superimpose the rays and see where the shadows would have been, and I could have done that before I ran the full analysis, but that's not research, is it? Learn as you go. Thank you. Any other question, remark? You mentioned the costs. What the costs are. If you are trying to measure something on a bridge, you would think that it's much cheaper to just measure it from where you are than to wait the satellite to run around.
Yeah, so one of the questions even the space community always asks me is, why would you want satellites when you can stick sensors on things? And the reality is, so my department in Cambridge is, I'm from two different departments. One's the Langer Rourke Centre for Construction, and the other is the Centre for Smart Infrastructure and Construction. So basically, we go around sticking sensors on everything. And one of the things people don't realize is actually it's not just the cost of sensors, which are becoming next to nothing, but actually the infrastructure around it to collect data, to transmit data, and all of that kind of associated cost. So two examples. One, Hammersmith Flyover. There was a period where I wasn't receiving any of the sensor data, and so I called up to try and figure out what was going wrong with the monitoring company, and it turned out that someone had just forgotten to pay an electricity bill. So then, so if you don't pay the electricity bill, then you can't store, collect, and transmit your data. So things like that happen, whereas I was still collecting the satellite data because that always has to pass around and then transmit the data back. And another example, what was I thinking about? Another example is the cost of diverting electricity when you're not in a city. So one of my colleagues was looking at a rail study for a bridge in a rural area of northern UK, and there was no electricity nearby. And so the asset owner asked, well, what would it cost to divert an electricity line? And it ranged from between 20,000 and 80,000 pounds, which is, I don't know, 25 to 90,000 euros, something like this. But thousands and like tens of thousands just to provide an electricity supply. So yeah, there are advantages and disadvantages. Satellites can't solve every problem, and they do have their own limitations. But I think it's all part of a kind of tool belt of structural inspection and investigation tools. Yeah. They all kind of complement each other and provide insights in different ways. So I don't think one of these answers all of the problems, but I think, say, for example, satellites could pick up a sign of unusual behavior and say, at least send someone to go visually inspect, or tell someone that maybe you should invest in a structural health monitoring scheme now. That's where I kind of see the advantage, not as a replacement.
Thank you very much. Any other question?
Yeah, so for the radar satellites, they're actively emitted and collected. So the other point is that they do transmit through clouds because they're an active sensor. These ones, when they pass certain points in the Earth, download the data. So there is a little bit of a lag, so you can't do instantaneous real-time monitoring, which actually is quite difficult for most monitoring systems. So it gets transmitted to the satellite owner. So, for example, Airbus or the German Aerospace Center. And then they collect that along with the precise orbit monitoring data. So as the satellite passes, if it's not exactly in a perfect line, it takes that data and you get both of those files together so that you can compensate for any effects in the orbit together with the image. And so that comes to you via a FTP download site and you download the imagery.
Any other question?
You mentioned just then that you couldn't do it in real time.
Yeah.
In the case of Tadcaster Bridge, where you saw the anomaly only a few days before, might there be a time where you could predict bridge collapse in those few days and stop it?
Well, I guess it depends what kind of bridge failure it is. If it comes to get it, like at the very least, you can at least close a bridge off to prevent some kind of disaster from happening. In Tadcaster, it was a good month and a half, 2 months before the collapse that there was a sign or a sign that there was something unusual happening, and that's where the advantage. If it is something instantaneous like a vehicle strike or something like that, or brittle failure of some variety, then no, it's not very helpful. This is something that would be able to assess something that shows a longer-term sign of a problem. Very often the techniques being used for settlement monitoring, things like that, or if someone's excavating in a nearby area and there's differential settlement, that comes up quite well. Water extraction, yeah, so in the case of tunneling, when you extract water, you can see the deformation around.
Thank you. Any other question, comment? Otherwise, Sakthy, thank you very much
Thank
for a
you.
very interesting presentation.